Okay, welcome back. So we've been working on some applied optimization problems, and when you get to number 7, you're going to see a problem similar to this one. And I want to walk you through this process because we're going to have to use a constraint on a relatively complicated formula to go ahead and achieve what they're asking us to find here. Okay, so we have a box with a square base and an open top that must have a volume of 108,000 cubic centimeters. We wish to find the dimensions of the box that will minimize the amount of material used. And then they're going to walk us through that process. So first, we're going to find a formula for the surface area of the box only in terms of x. And x is the length of one side of the square base. The hint is to use the volume to express the height of the base in terms of x. That's called the constraint, and we will set that up in a second here. Once we do that, we're going to have a simplified formula for the area, right? The surface area is how you find the amount of material used. So we're going to have a formula for the surface area, a of x. We're going to find the derivative. Then we're going to set that derivative equal to 0 and find our critical number. And then to make sure we find that minimum, we are going to use the second derivative, okay? So that's our plan. Now, let's just see how that fits with what we had for our written out steps. So step 1, we're going to create or identify the objective function. Well, in this case, the thing that we want to minimize is the amount of material used. Let me undo that thing and make that a little more narrow. Okay, the amount of material used. There we go. In our case, that's our area function, a of x. Okay, so that's a surface area. We want to minimize the surface area. If need be, if there are 2 or more variables, we're going to use a constraint to get rid of one of the variables. So let me show you that we are going to need this in this case. Typically what you do when there's some sort of object involved is you try and draw a picture and label it with variables. So in this case, we're working with a box. So the box is going to look something like this. I'm not the greatest artist, but basically it has a square base. That means a square bottom. And they told us that the measurement on the bottom is x, right? It says right here, the length of one side of the base is x. So these measurements here are both supposed to be the same when I draw this thing. That bottom is supposed to be a square. And then, of course, a box also has a tall part, a side, and a height. And so here's what that looks like. Now, we can't call that x because we don't know for sure if it's the same measurement as the base. So I usually just call that h. And then what I do know is the volume of this thing has to be, 108 cubic centimeters. So if you look over at this picture, we can quickly calculate the volume, right? From geometry class, I hope you remember that the volume of a box is length, is length times width times height. So for us, that's x times h, and that would be simplified as x squared h. And then we know our volume is 108 cubic centimeters, so we know that the formula x squared times h equals 108,000. This sucker right here is our constraint. It's the thing that we're going to use to eliminate variables, just like the hint says. The hint says, use the volume formula to express the height in terms of x. That means solve for h. So if you go over here to your constraint and you solve for h, all you really need to do is divide both sides by x squared. Using the wrong pen again. Using the wrong color again. Divide both sides by x squared, and we get h equals 108,000 over x squared. 108,000 over x squared. So this is now our constraint. Okay? We're going to use that to eliminate variables. I'm going to label that just so we know this is a constraint. I'm using the wrong pen, sorry. Okay. All right, so we've got the constraint now, but we want to use this to set up our objective function. So let's remember what that is. That's supposed to be the surface area of this thing. So now on my picture, let's go ahead and write out our objective function. The surface area is basically the area of all the sides of this box. So this box has a bottom and then 4 sides. There is no top. So the box has area here, and it has area on all these sides, okay? The way you figure out area is just to multiply length times width. So the area of the bottom is x times x, which is x squared. The area of each side is x times h, right? That's this thing right here. X times h gives you the area of that. And there are 4 of those, so we typically write that as 4 xh. And then, as you can see, my objective function, right? This is my objective function. It has too many variables. We need to eliminate the h, and that's where this comes in, right? So eliminating h, our area function, our objective function, becomes x squared plus 4x times 108,000 over x squared. And then the question says to put in a simplified form, right? It says simplify right here. So I'm just going to do a little bit of math, and the little bit of math I'm going to do is I'm going to just clean this up a little bit. So when you multiply 4x times 108,000 over x squared, you do 4 times 108, and I believe that's going to be 432,000. Let's see if I'm right. Yeah, I'm right. Okay, 432,000. And then when you multiply x by 1 over x squared, you get x on the bottom. So this simplifies to 432,000 over x with a plus sign. And this is our objective function that we're going to put in for the answer. X squared plus 432,000 over x. When you do this problem, the only thing that's probably going to be different is the 432,000, because you're going to have a different number for the constraint. But the rest of the math is going to be very similar. So just don't panic, just follow the plan. I'm trying to help you get there. All right, the next thing we're asked to do is find that derivative. So we need to take the derivative of a of x. Before we do that, let's rewrite it as a power function or a polynomial so that we can quickly use our power rule. So 432,000 over x becomes 432,000 times x to the negative 1. And then when you do the derivative, you do the power rule on x squared and you get 2x. And you do the power rule on 432,000 x to the negative 1, and you get minus 432,000 x to the negative 2, right? Negative 1 minus 1 is negative 2. And then we usually simplify this and write it without the negative exponent, so something like 432,000 over x squared. And this is what we'll type in for our derivative answer. Again, the only thing that's really going to change for you is the 432,000. But the derivative over here is 2x minus 432,000 over x squared. There's my derivative. Now we have to set it equal to 0 and get our critical number. And they're giving us a hint that you multiply both sides by x squared. So let me just show you how that works. So we're going to set this equal to 0 and solve. I can also show you on decimals if you want to see how we solve it that way. But let's just go ahead and do this thing. So we're going to set 2x minus 432,000 over x squared equals 0. We set it equal to 0. I'm going to add the 432,000 over x squared to both sides, and I end up getting this. And then I'll do the hint they said, which is multiply both sides by x squared. So if I multiply both sides by x squared, keeping in mind that x can't be 0 anyway because it's a measurement, we end up getting 2x cubed equals 432,000. And you divide both sides by 2, and I think we end up getting 216,000. X cubed equals 216,000. And then we just do the cube root of both sides. And I believe that's 60. So what that's telling me is that the measurement for the base is 60 centimeters. Now, that's our only critical number that we're coming up with. But we still have to check and see if that is a minimum, right? And that's why they want us to test out this second derivative. So right here, I'm going to put 60. But we next have to make sure that this value is a minimum. So let's find the second derivative, right? That's what they're asking us to do right here. So I go back over to my first derivative. I'm just going to run through the derivative again. Let's do it right here, okay? And so the second derivative, I'm going to use the power rule. And the derivative of 2x is just 2. And then when you bring the negative 2 down, that makes a positive 2. Positive 2 times 432,000, which is 864,000. So it's 2 plus 864,000 x to the negative 3. And so that's going to look like 864,000 over x cubed. Not the greatest handwriting in this video today, but hopefully you can get the gist of this. All right, so that's our second derivative. Let's write that in. It was 2 plus 864,000 over x cubed. And the last thing they want us to do is evaluate our second derivative with that x coordinate that we found. So they want us to plug in 60. So the math is going to look like this. I'll go back over here and just plug that in. The math that they want us to do is like this. The second derivative with 60 plugged in is 2 plus 864,000 over 60 cubed, which we already know is 216,000. But that's what they want us to do. So that's going to be 2 plus 864,000 over 216,000. And we can figure out the actual number. Do they want us to actually put the value in there? I guess they do. So they want the actual number. Usually all I do is look to see if it's positive or not, because if it's positive, we have a minimum. But let's go ahead and get this. I'm going to crank it out with my calculator here. I'm just going to cross out these zeros and do 864 divided by 216 and see what I get. It's probably an easy answer, but my brain's not working. It's 4. Of course it is. So this value is 2 plus 4, which is 6. Okay, so that's the number we're going to type in for our last answer, but I want to tell you why this is important. The value of 6 isn't really as interesting to us as the fact that this is positive. Because when the second derivative is positive, the function is concave up. And that means that our point there is a minimum, okay? So when you have a concave up function on a critical number that you found by setting the derivative equal to 0, that's the second derivative test, you know you have a minimum. So they want us to put the 6 in the answer blank, which is what I'm going to do. But the real important part is that we know this is a minimum because this is positive. Okay. All right, so let's take a look at what we've done here, and I'm going to wrap this video up. And you're going to have a similar problem with just a different number here. But the idea is we have this open top box. The constraint is given to us as volume. And so what we did is we drew the box and figured out the formula for the volume, which we have right here. Let me just highlight that, and I'll do that in yellow here. So here's our original formula for the volume, but it had the V in there, and so we put the 108 in because we know the volume. So that gives us our constraint down here, and we use this constraint, h equals 108,000 over x squared, to eliminate variables in our objective function. Let me tell you where the objective function came from again. We are trying to minimize material used, and the way we're going to do that algebraically is we're going to minimize the surface area. So this word here is the same. It's representing the material used. The surface area is representing the material used. So we're going to minimize that. Remember, the objective function is the thing you want to optimize. So we figured out the area of each of these sides, right? There's a bottom surface and there are 4 side surfaces. And that was x squared plus 4xh. But to eliminate the variables, we had to use our constraint, and we ended up right here with this. This was our objective function. Then we had to find the derivative, and then we had to set it equal to 0 and find our critical points or our critical numbers. We didn't really find the point because we didn't do the y value. We just found the x value. But we found this critical number here. And then we plugged it into second derivative and made sure it was positive, made sure it was a minimum. And that's how we filled in the boxes. So you'll do the same thing with the problem that you're working on. The only real difference is the 108,000 will change to a different value. So very few things are going to change in terms of your answers. But see if you can follow this process. I know this is a challenging problem, but I think if you stick with it and kind of follow what I did here, you can get it done. All right. That's it for me for now, but you know where to find me if you need anything. In the meantime, take care.